Hello friends, today we will see design of moment resisting base. This is the numerical for which we will be designing moment resisting base. Design a slab base for a column ISHB 250 subjected to factored axial load of 500 kilonewton and a factor bending moment of 45 kilonewton meter. Use M25 grade of concrete and Fe410 steel. So here the external loads are given acting on the column 500 kilonewton and 45 kilonewton meter. The column for which this base is to be designed is ISHB 250. Now before we proceed further, I will just take you through what exactly happened when the column is subjected to bending moment along with axial force. So let's say this is the column and it is subjected to initially only axial load. Now, when it is subjected to axial load alone, then in that case, the upward soil pressure distribution it will be uniform. So it will be uniform throughout. But when this axial load is accompanied by a bending moment, so in that case, upward soil pressure distribution will depend on eccentricity value and d value. Now d is nothing but width of this base plate. In the first case, here E is equal to D by 6. The eccentricity value you can calculate by moment divided by E. Now, depending on relation between E and D, there are different cases of pressure distribution. Then this second case where E is less than D by 6, and the last one where E will be greater than D by 6. These are the three different cases. Now out of these three, so here there is no tension in first case. In second case also there will be no tension, but in third case, the some part of base plate will be subjected to tension. So as far as possible, the design should be so as to avoid tension at any position of the cross section. So there can be two options, either E equal to D by 6 or E is less than D by 6. For ease in calculations, you can continue with E equal to D0. At left end, it will be P minimum. Here, right end, it is P maximum. So these are the values. So likewise, you will have to proceed with for design of isolated this moment resisting base. So now we'll continue with this numerical. So here we'll note down the given values first. Pu equal to 500 kilonewton and EMU equal to 45 kilonewton meter. Now the first step will go for calculation of base area of base plate required, area of base plate required. This is equal to Pu divided by 0.45 FCK. So 0.45 FCK is the bearing capacity of concrete. As per IS code, maximum value is 0.6, but for higher margin, safety margin, it will be taken as 0.45 FCK. Now, this particular expression is valid for axial load only when column is subjected to axial load only. But when column is subjected to bending moment along with axial load, now to account the effect of that bending moment, we will add this factor 2 so that we will get the appropriate approximate area of base plate required. Where 2 into Pu value is 500 kilonewton, then 0.45 FCK. So in the problem statement, it is mentioned that M25 grade of concrete is to be used. So that will be 25. So once you put all the values in this expression, you will be able to find out area of base plate required. So this comes out to be 888 mm². So this is the required area of base plate. Now, so you have to decide whether you are going for E equal to d by 6 or E less than d by 6, because based on that only we need to find out plant dimensions of base plate. Plant dimensions of base plate you have to calculate. Now for this, let us we will go for the case E equal to d by 6. Now first we will calculate E value. So E equal to Pu mu divided by Pu, mu divided by Pu. So mu is 45, 6 divided by Pu value is 500, 10 raised to 3. So this comes out to be 90 mm. So from this D will be 6 into E. So 6 multiplied by 90, which will be 540 mm. So one dimension or width of this plate comes out to be 540. Now we have to decide another dimension. Let's say this is the base plate. So one dimension we have got here is 540. If you see the column, it's having depth 250, and this column will have certain flange width as well. So according to the requirements, you have to decide the another dimension of base plate. Now area required is with us. So area will be equal to B into D. So here B value is 540. So B value already is with us. It's 540, and accordingly you have to D value is 540. You have to find out B value. So this is equal to 888.8 mm². Right. Now next you have to find out B value. If you divide this right hand side by D value, which is 540, you will be getting the value of B, approximate value, which is 164 approximate value EM. But as far as possible, this 164, if you provide here, you cannot accommodate. So likely water connection is to be done. So you have to accommodate anchor bolts as well. Now this flange weight is to be accommodated as well. So that's why this 164 is not going to be sufficient. So we will make it 400 mm. So that's why the plant dimensions, though area required is very less, but to accommodate flange width as well as these four anchor bolts on base plate, you will have to increase the another dimension of base plate, which is required 164 only, but we will make it 400. So therefore provide base plate of size 400 by 540. Now once this is done, now next you have to go for calculation of upward pressure. Calculation of upward pressure. Now say this is the base plate and below you are getting upward pressure. Here it is P minimum and P maximum. Now, when column is subjected to combined forces, that is bending moment and axial force, so this P minimum, this will be equal to axial stress minus bending stress. No doubt in this case, as we are using E equal to D by 6, P minimum will be 0. Then P maximum, so this will be equal to again axial stress plus bending stress. So P max will be equal to axial stress will be Pu divided by area of plate plus bending stress will be Mu divided by Z. Now, area of base plate provided is 400 multiplied by 540, which comes out to be 216,000 mm square. Then Z section modulus BD square by 6. This will be 400 into 540 square by 6. So this comes out to be 19.44 into 10 raised to 6 mm. So putting these values, you will be able to find out P max value 500 into 10 raised to 3 divided by 216,000 plus mu value is 45 divided by 19.44 10 raised to 6. So this P max value, this comes out to be 4.62 Newton per mm. Now to get the thickness of base plate, first you will have to locate the critical section. Now the critical section will be present at this level. So this is the location of critical section, and this remaining portion will behave as a cantilever or overhanging portion. And whatever upward pressure is acting, it will cause bending moment at critical section, and to resist that bending moment, thickness of base plate to be provided. So we will have to first calculate that X value. Now to calculate X, this X we can calculate. Suppose this base plate is there, and in between the column is provided, and this is the critical section location X. Now to get this, what we can do, so we will have to consider half of base plate, which is 540 divided by 2, and then you have to deduct half the depth of column. Now half the depth of column, so this is 250 divided by 2, because ISHB 250 is the column. So X value will be 540 by 2, which is 270 minus 250 by 2, 125. So this X comes out to be 1:45 am. I hope you are getting the things. So this total base plate, if you consider, so over this length, the section is critical, and at the junction, at this particular location, it is located, critical section. So we have to find out this Vx. Now, the base plate will be subjected to upward soil pressure here. In this particular portion, now this is behaving as a cantilever on right hand side, and it is subjected to upward soil pressure. Now that intensity already we have calculated, it is 4.62 kilonewton. Now next you have to go for calculation of bending moment at critical section. So we will assume unit width. So we will assume unit width here. So that's why this pressure will be converted into UDL. Whatever this upward pressure is there, this will be converted into UDL. So it will be 4.62 Newton per mm square multiplied by 1 mm. Accordingly, we can convert it. So let us calculate bending moment at critical section EMX. So this is equal to half. So here you have to remember that. So it is subjected to trapezoidal portion because the pressure distribution is not uniform. It is going to be varying. So this is the base plate, and you will be getting upward soil pressure here, and critical section is located somewhere here. So you will have to first calculate the pressure intensity at the critical section. Here it is 4.62. This distance is 145. So you will have to calculate the pressure intensity at critical section. So Px we will call it as, this is P maximum. So you will have to use concept of similar triangles, and from that you will have to calculate first the pressure intensity at critical section. So using similar triangles, this total distance is 540 mm. So total distance is 540. So P max divided by 540. So this has to be equal to Px divided by the distance there, 395. So from that you will be able to find out Px value, which will be equal to 3.37. Then you will be able to calculate bending moment at critical section. So here you can convert this loading into two segments, one rectangular portion part 1 and one triangular portion part 2. The bending moment at critical section will be because of these two divided load segments, one rectangular and one triangular. So first we will go for this rectangular portion which is having pressure intensity Px equal to 3.37. So Mx equal to 3.37 multiplied by 145 into 145 divided by 2. So similar to UDL, this expression will be there, plus because of the triangular portion. So first we will calculate the load. Half base is 145 into height, that is intensity 1.25, multiplied by centroidal distance. So as centroidal will be here somewhere, so this distance will be 2/3 of 145. So we will multiply it with total load. So bending moment at critical section, after simplifying, this comes out to be 44.18 Newton meter. Now this external bending moment has to be equated with moment of resistance of section, which is given by 1.2 multiplied by Z into Fy upon gamma m0. So 1.2 Z is Bt square by 6. We have assumed B as unity into Fy upon gamma m0. So moment of resistance we will equate with external bending moment, or because of upward pressure, is 44.18 into 10 raised to 3. This is equal to 1.2 into unit width 1 into T, that itself we have to calculate by 6 into 250 upon gamma m0 1.1. After simplifying this, T comes out to be approximately 38 mm. So you can make it 40 because this 38 mm plate will not be available in market. So you can make it 40. So the overall dimensions of base plate will be now. So base plate size will be 400 by 540 by 40. So this is the dimensions of base plate. Now you have to go for connection design. So you will have to check the stresses, whether those are compressive or tensile in nature. So the axial stress in column, axial stress in column. So this is equal to Pu divided by area. So 500 into 10 raised to 3. So for ISHB 250, area is 6496. You can take it from steel table. So this comes out to be 76.97 Newton per mm. Similarly, you have to calculate bending stress in column, bending stress in column, which is equal to mu divided by z. So 45 into 10 raised to z value, again you will be getting from steel table. This comes out to be 72.7 Newton per mm. Now the net stresses acting on column section are compressive on either span, entire span. If you consider entire span of column, so it is subjected to totally compression. Therefore, the weld is required only to hold base plate and column in position. When we talk about connection between base plate and column, it is just required to hold the column and base plate intact in connection with each other. As the column is not subjected to tension at any span throughout the length, so the connection needs to just keep these two things in connection. Now, for connection, you have to provide a nominal weld. You have to provide a nominal weld for connection. So let us provide 6 mm fillet weld, 6 mm fillet weld for connection between column and base plate throughout the periphery of column, throughout the periphery of column. Then next, connection between base plate and concrete pedestal, base plate and concrete pedestal. The earlier was between base plate and column, and this one is between pedestal and base plate. Now for this connection, since there is no tension in entire base plate portion, again anchor bolts are need not to specifically designed. So nominal anchor bolts can be provided. So you can provide 4 number M20 anchor bolts, M20 nominal anchor bolts for connection between base plate and concrete pedestal. Now, if at all there is tension in base plate, in that case, definitely these anchor bolts needs to be designed specifically to resist tension. Now, finally, you will have to draw the design sketch for this. So this is the column section ISHB 250. It's going to be base plate, and this entire assembly is resting on concrete pedestal. Now the concrete pedestal, its width you have to select judiciously. The design of concrete pedestal we will cover in next video. This is going to be the concrete pedestal. How to decide its depth we will see in next video. And there are anchor bolts provided for connection between. So these are anchor bolts. So this is column ISHB 250, base plate, dimensions 400 by 540 by 40. So after completing design details or design sketch, this numerical completes here. So you have to start with area required, then dimensions, plan dimensions of base plate, then you have to calculate thickness, and finally you have to complete the connection design. So this is the sequence to design moment resisting base. I hope you understood the things in this lecture. Thank you. We'll meet with next topic in next video.